Good morning, everybody. We are back with our next unit on acoustic phonetics. This is module 13 on acoustics of voice and its auditory correlates. Just to understand how do we hear. Actually, hearing is a very complex process. It's a very complex neurocognitive process and neurosensory process. But we are not going into all those biochemical and bioelectrical processes involved. What we are looking at is the physics of voice and the three most important properties, which are frequency, intensity, and the waveform, meaning time. And we want to see how each one of these three are received by the human ear, how they are heard. So the auditory correlates that we want to look at is pitch, the way we hear frequency, and loudness as the auditory correlate of intensity, and quality, which is the auditory correlate of waveform. Pitch, intensity, and quality, these three aspects, although they belong to the domain of auditory phonetics, but they are absolutely crucial even to understand the acoustic properties of voice and acoustic properties of speech sounds. And they are extremely important because how we hear is a great mystery. I mean, how our mind works on the speech sounds is a great mystery, and people are still working on it, and lots of scientists from different disciplines are engaged in, understanding this mystery, trying to unfold the underlying reality. But the fact is that two sound waves, even if they are of the same pitch, produced by the same voice, they can be heard very different if the intensity varies. They can also be heard very differently if the quality varies. Similarly, two sounds of the same intensity, if the pitch varies, they are different. If quality varies, they are different. And the third one, two sound waves of the same quality can be heard as different if either of the other two pitch or intensity varies. So let's look at these one by one. Frequency heard as pitch. Now, a complex wave, what we get in the oropharyngeal chamber and what we get after all the resonance processes, after the oropharyngeal chamber has provided all the resonance and filter process to it, then what we get is something like what you see on the screen. This is the spectrum of a complex wave, which may have frequencies and with the individual with respective amplitudes exhibited on this screen. Simple waves or the peaks are heard as pure tones. Simple sine wave is heard as pure tone, higher frequency heard as higher pitch. That's the simple formula. But if you want to say how much higher is the frequency and how much higher is the pitch, then it's not a one-to-one correlation, and this is what we need to understand, how it happens. Complex waves with a peak spectrum or a flat spectrum, we find that pitch corresponds to the peak or the average of the frequencies if it's a flat spectrum. Complex periodic repetitive waves may have constituents like, let's say 250, 500, 1000 and 2500 hertz. If there are four such sound waves combined, then the resultant wave, the pitch will correspond to the highest common denominator, because the ultimate resultant wave will have that frequency of vibration, so that frequency. So 250 hertz will probably be something contributing to what we are hearing. Now, we have seen this slide before when we were talking about acoustics of voice. The frequencies, now these three kinds of spectral representations are those for male voice and a female voice and a child's voice. So male voices, if the lines are too close, it only shows that the fundamental tone of voice is a lower frequency, and if it is something around 100, then all the whole number multiples will be 200, 300, 400, all of that. Then in case of a female voice, if it is around 200, then the harmonics will be 2, 4, 6, 8, and children's voices could be 3, 6, 9, 12, and so on. So this is a spectral representation, and what we hear, the male voices as low-pitched voices, you can instinctively make a difference between a male voice and a female voice. Female voice has a slightly higher pitch, and children's voices are really much higher than the other two voices. The human auditory range is 20 hertz to 20,000 hertz, that we all know. And less than 20 hertz are infrasonic sound waves, more than 20,000 hertz is ultrasonic sound waves. And although even in this broad kind of a very wide range of frequencies that we hear, human hearing in the lower range is much better than hearing in the higher range. In the lower range, you can make a distinction, just heard difference of, let's say, 3, 4 hertz, or even 5 hertz, 7 hertz. Even that one can distinguish, between. But in higher frequencies, the higher frequencies are clubbed together. So it's a much wider range of frequencies put together. Till you hear the next pitch, it is the next bundle of frequencies. So male, female children's voices are heard as distinct because they are all in the lower range, 100 to, or let's say from 50 hertz to, for a very, very low pitch, 50 hertz to very high pitch, maybe 350 hertz. But we hear much more than human voices. As far as human voices are concerned, even small distinctions, a small variation in pitch, which becomes a tone, it could be 10, 20 hertz variation, it becomes high tone or a low tone or a falling tone. All these are heard very distinctly. But when it comes to, thousands, 5,000, 7,000, they are clubbed together. You make a larger difference between the frequencies, only then you hear the next pitch. So, Mel scale shows how up to 1,000 probably we will have some kind of a direct correlation between the increase in frequency leading to increase in pitch. Up to 1,000 you can find a direct correlation. After 1,000 you can see the curve bending, just to show that it's a much larger frequency required, or larger frequency change required to be able to hear the next higher pitch. And this is another representation where you find the musical notes are, clubbing of certain range of frequencies. So if you make a distinction between, something like 880, then on the y-axis it will not be 880, it will be less of difference. Similarly, from 880 to 1760, see the huge difference that you are making in frequency in hertz, and on y-axis you will see a little bit of difference, or the next higher pitch is heard. It's a scale which we have to work very differently, but basic principle is higher frequency would lead to higher pitch. In the higher frequencies range, it will be much larger clubbing of frequencies heard as a single pitch. Now let's go over to the second. We come back to pitch once we understand the loudness part, and then we see how we hear pitch and loudness together. Now, amplitude of the sound wave, amplitude square is intensity, amplitude of the sound wave or intensity is heard as loudness, which means the amount of energy that has gone into producing the sound. And that energy translates as loudness. What we hear is high energy sounds, higher loudness. Now, amplitude can be measured in dynes per square centimeter, power in terms of watts per square centimeter, used or defined in physics. But as far as our hearing is concerned, we do not have a unit defined in absolute terms. It is only in relative terms that we find that this sound is louder than the just audible sound, which may be the reference point. So what we do is we identify two reference points there. The lowest is maybe the flicker of a petal, very, very soft kind of a sound, just audible sound. Just audible sound. If that is the reference, then the next higher, relatively higher pitch would be, let's say, if that is 10 raised to the power 1, the other one could be 10 raised to the power 2. So that should be about 10 times louder, 10 times higher intensity, and so on. So on the other end of the scale, you have to have the loudest that you can possibly hear without causing pain to the ear, which means the threshold of pain is the next higher limit. Within this, we have a scale, and this power ratio, as I just mentioned, if 10 to 1 is common logarithm of power ratio 1, then difference in decibels is considered as 10. 10 raised to the power 2, the next higher level of loudness, is written as 20. 10 raised to the power 3, meaning, so you are adding on 1 0, multiplying it by 10 every time. Look at the first column. This is given by Ladefoged 1962 on page 82, just to show in a simplified version of what is the relationship power ratio between sounds, and what is the common logarithm of power ratio, and then the difference in decibels. So decibel is a unit of loudness which is in relative terms and not in absolute terms. So intensity or power as loudness. So we want to understand how much is the power of the two sounds which are heard as, different, distinct loudness. So, amplitude is doubled as 2x, that is power is x square increased by a factor of 2 squared. And if the amplitude is 3x, then power is x3, which is increased 9 times. So decibels of loudness can be seen like this. This is a nice picture we got from the website of noise monitoring services.com, and a good way of comparing the from hearing threshold from the very the lowest or the softest sound at 10 decibels to going up to 140 decibels. So 10, 20, 30 would actually mean adding more zeros to it, or everything multiplied by 10. So 10 raised to the power 14 is 140 decibels. Similarly, here is another representation. The source of noise is given roughly. The moderate, there are a few, in the 10, 20, 30 decibel range, you find that they are kind of moderate intensity sounds with decibels in 30 or 40. Then louder sounds are in the range of 50 to 70 decibels, and then we go extremely loud and painful. So this is how the actually threshold of pain is something like 120, and if you are exposed to 120 decibels, maybe working as a DJ, working in a club, and or working in a factory where you are exposed to loud sounds, all day, then you can lose the ability to hear the lower intensity sounds in course of time. Now, pitch and intensity, since the two things are always together, a sound wave has a certain frequency and certain amplitude, and therefore the two things, a sound wave is heard as a composite one, So the two things heard together, this particular diagram, this is again from Ladefoged, and this figure shows that some of the very low frequencies may not be heard unless they have a little higher intensity. Similarly, a very, very low on decibel scale, a very soft sound and a lower decibel sound has to have at least a higher frequency to be heard. And then the threshold of pain is around 130 decibels or around that. And the core area in the 50 to 60 decibel and about 1000 frequency zone. The core, the central area is a comfortable auditory zone, auditory area. The speech sounds are located in the still smaller, narrower, core of this. The third feature is the waveform or the time factor. Time wave in the time domain, it will carry the properties of what kind of a quality of waveform is there. Now this leads to, the waveform leads to what we hear as a very, very subjective matter, subjective property, and that is quality or timbre of the sound wave. So sometimes when the frequencies of the two sounds are the same and intensity is also the same, but the two can be different. If one is produced by a string instrument and the other is produced by a resonating air column, two different kinds of instruments producing two sounds, they are very different. The difference in quality can be attributed to the complexity of the waveform. Now here, as far as speech sounds are concerned, we have this another representation here. These are three different vowel sounds. When the author, meaning Ladefoged here, he pronounced three different vowel sounds: o as in cot, and u and e. So e, u, and o. The three, let's say, three in a triangle, the front high and the back high vowel and the open back vowel o. So these three had a fundamental frequency of approximately 100 hertz pronounced by the same person with, keeping the pitch constant. But even then, you can see that vowel O has a very different kind of a waveform from the other two. So that seems to be having a different quality, different timbre, which is perceived as very, very distinct and different. So quality or timbre, as we hear, can be attributed to wave shapes. And therefore, we've just seen the example, qualitatively they can be very different. Now, coming to the towards the end of this unit, when you want to test your hearing, you go to a clinic and the audiologist tells you that let's draw an audiogram for your hearing. Then they conduct a certain test in the audiography, and what you get is something like what you see on this screen. It is the same as what we had seen before, pitch and intensity heard together. Quality for this purpose is ignored. Once you hear the pitch, once you hear the frequency and the amplitude, once you catch that, the quality comes only after that. So these two parameters are considered here in an audiogram, and you can see on the x-axis you have low to high frequencies from left to right, and decibel scale is from the highest point to the lowest. They have 0 on top, and loudest sounds are going down on the scale. So what you see is that if you can hear a pure tone fed to your ears in a quiet and room, in a soundproof room, you should be able to hear that even if it is 10 decibels or 20 decibels. But if you don't hear it in the 10 or 20 decibels, you go over to 30 and 40, you find that this is an indication of a mild hearing loss. Then you go over to 50 and 60, then this is moderate hearing loss. Then it's alarming. And 60 onwards, it is moderate or moderately severe hearing loss. This is how they define it. And 70 to 80 is your severe hearing loss. So this audiogram helps you, decipher what kind of, what is the level of damage or deficit, which may have happened because of your service conditions. You may be working in a factory every day. You are in a very, very loud environment, so you don't hear the lower range, in the lower decibel range, and that can happen. And this module combined with the larynx as the source of sound, the module number 12. The two modules together give you the practically acoustics of voice and how the voice is received. Thank you very much.